So, page 152, we have changed to a different part of the Eurocode. So we are now considering 1993-1.8. And 1993-1.8 covers joints. This is an overview of the things that we find in 1993-1.8. We have a lot of information about the strength of components. So the strengths of bolts, the strength of welds, the strength of plates. We have a large section on how you calculate the moment resistance of a connection. We have a large section on how you calculate the stiffness of a connection. And I would say in the UK, this is brand new. In the UK, we have never calculated the stiffness of a connection. And there is also a large section in 1993-1.8 which covers the joints between hollow sections. I believe that to check the resistance of a joint between hollow sections is the responsibility of a designer. A designer has chosen the sections, a designer knows the loads in the members, a designer has arranged the geometry of the joint, and therefore the designer has set the joint's resistance. There is nothing the steelwork contractor can do. He can only check the joint resistance, and if it is not sufficient, he must strengthen it. A really important feature in the Eurocode is that connections require classification. The Eurocode says that we can classify connections by stiffness, and that would be important for elastic design. We can classify them by strength, and we would be interested in strength for plastic design, or both. And when we classify a connection, we might find that the joint is nominally pinned, or at the other extreme, we might find it's rigid, or perhaps you would refer to it as continuous, or somewhere in the middle, you would find it to be semi-rigid. Now, although we are in 1993-1.8, I'm just going to move back for one brief moment to the main part of the structural Eurocode for steel, 1993-1.1. So when we are undertaking our analysis in accordance with 1993-1.1, the Eurocode says we must know about the behaviour of our joints. We must know whether they are nominally pinned, or whether they are continuous, or whether they are somewhere in the middle. Because if they are nominally pinned or rigid, then we can make assumptions about them in the analysis. But if they are semi-rigid, we need to account for their behaviour when we are undertaking the analysis. So, for example, you might introduce springs into your analysis model. So the Eurocode says, if we have nominally pinned or rigid connections, then we can neglect it in the analysis. We can model as a perfect pin or perfectly built in. But if we have semi-rigid connections or semi-continuous connections, we would have to allow for that in the analysis, maybe by introducing a spring into our frame analysis. And the Eurocode asks the question to us as designers, are the effects significant? And we must answer that question to know whether we need to model in the analysis or whether we can afford to ignore it. In the UK, we would always be down this side. In the UK, from birth, every engineer knows that the connection is either pinned or continuous. And we know that from birth without doing calculations. Because in the UK, we can look at a connection and we can say, that's pinned, or that's continuous. We have never ever done any calculations to demonstrate that they are pinned or continuous. So the process in the UK is generally to assume that connections are pinned and then make sure that when they are detailed, they achieve the assumptions made in design. Or alternatively, to assume that they are rigid and then make sure that the joint behaves as a rigid joint. Now, that may be important because for a moment-resisting connection that we have assumed is rigid, perhaps we do not design just for strength, but we also consider stiffness to make sure that the assumptions made in our design were correct. In the UK, we would never be modelling semi-rigid or semi-continuous connections. We don't know anything about the stiffness of our connections. So here are the classifications. This is by strength. A nominally pinned connection must accept the rotations because we are designing the beam as a pin-ended beam. We expect the connection to rotate. And therefore the connection must be ductile. So something must behave in an elastic manner. And that will not be the welds. Welds are not very ductile. But plates which flex are ductile. So for example, an end plate connection would be a good example of a nominally pinned connection. If we are classifying by strength, then full strength is obvious. It must be stronger than the connected members. If we are classifying by stiffness, then this is moment rotation on the vertical axis. Sorry, this is moment resistance on the vertical axis. This is rotation on the horizontal axis. So the Eurocode tells us where the limits are between a nominally pinned connection and a semi-rigid connection. It tells us where the limit is between a semi-rigid connection and a fully rigid connection. And then it gives us a method to calculate the stiffness of our connection so that we can demonstrate that we really are nominally pinned, or that we really are nominally rigid, or that we are in this grey zone somewhere in the middle. And that, to the UK eye, is a long and laborious process which we do not trust. The process involves calculating the stiffness coefficient of all the components that you find in the joint. So these are some of the components that you find in the joint. And for each one of these, you would need to calculate the stiffness. And then you follow the Eurocode rules and you assemble the different stiffnesses, and that will give you an overall stiffness for the joint. So the vertical axis again is moment resistance, the horizontal axis is rotation, and possibly this might be the way that a real connection behaves. So the Eurocode says if the applied moment is no more than 2/3 of the moment resistance, then the stiffness of the connection is the initial stiffness. But if the applied moment is more than 2/3 of the moment resistance of the joint, then there is a further adjustment to make to the calculated stiffness of the joint. In the UK, we do not do this, we have no software to do it, and we are very sceptical about the results. There is one worked example that I am aware of. It is a beam. It has a partial depth end plate. The end plate is only 8 millimeters thick. The end plate is not welded to the flanges, and the bolts are set 150 millimeters apart. 17 pages of calculations later, the Eurocode advises that the connection is semi-rigid. And that would be a good example why we in the UK do not believe the Eurocode. Because we look at that connection and we say that is a nominally pinned connection. whatever the Eurocode says. So now for the good news then. The Eurocode does not insist that we perform calculations. The Eurocode does say that we can classify on experience of previous satisfactory performance. So if somebody said to me, David, please demonstrate that your connection is pinned, I would put my hand in the air and I would say, I have previous satisfactory experience of this connection and I know that it is pinned. And I would try not to laugh, I would try to say that seriously. In the UK, we have some further assistance because our national annex helps us to decide if our connection is a nominally pinned connection or a nominally rigid connection. So we have two design guides in the UK. The first one covers nominally pinned connections. The second one covers moment-resisting connections. And our national annex says, if you design in accordance with the principles in this one, they are pinned. In accordance with the principles of this one, they are rigid, without doing any calculations. But clearly, that has no contribution in the Ukraine. Do those sentences make sense? I found them on Google Translate, so I have no idea whether they say the right thing. So in the Ukraine, you would either have to calculate, or without smiling, you would have to say, I have previous satisfactory performance, and I know this connection is pinned, or I know this connection is rigid. My advice to you would be only calculate if you have to. And I think if you do calculate, you'll find that your connections are stiffer than you thought they might be. You might be surprised to find how stiff the calculations declare your connections to be. So, lots of information in this part of the Eurocode about component strengths, and that will be important because 1993-1.8 says joint design is a component-based approach. And a component-based approach means that we look for the weakest link within the connection, and that sets the resistance of the connection. So we will need to identify a load path. How does the shear get from the beam into the column? Through the weld, through the plate, through the bolts. And we would check each one of those components. The resistance of the connection is the weakest one of those components. The Eurocode has some good practical advice. It says that when we create our load path through the connection, we must observe proper physics. So stiff areas of the connection attract more load. And we should reflect that when we create the load path. We need to respect those elements of the connection which are not ductile. So particularly, welds are brittle, and we need to make sure that they are not the weak link, because we do not want the connection to fail in a brittle way. When we look at component strengths, we will be carrying out some calculation, and then we will be dividing the characteristic resistance by a partial safety factor. And the partial safety factor will be taken from the national annex. These are the recommended values of the partial safety factor, and they are accepted by the Ukraine National Annex. And the most important partial safety factor for bolts, for welds, for plates is a gamma M2 of 1.25. You ought to take care, ladies and gentlemen, because this... This is the second time we've met gamma M2. We saw it yesterday, and we used it when we were checking members' intention. We had to check a gross area and a net area. And you remember when we checked the net area, we used the ultimate strength, and we divided by gamma M2. Today, when we work out component resistances, we are also using gamma M2, and just by chance, gamma M2 has the same value. But that's not necessarily the case. In the United Kingdom, gamma M2 in the connections part of the Eurocode is 1.25, but in the main part of the Eurocode that we saw yesterday, gamma M2 is taken as 1.1. So, in general, you must be aware that the same factor, gamma M2, can appear in different parts of the Eurocode, and although it has the same name, it might have a different value. In the Ukraine, gamma M2 in this part and the main part did have the same value, but in general, you should take care to make sure you use the appropriate national annex to tell you what the value is. So we're going to consider bolts and welds and plates. And you might find it helpful to look on page 73 of this guide. The table that you will find on page 70 of your guide is also very helpful, because in that table there is a list of different connection types, and for the different connection types it describes the things that you should check. So this table is talking about bolted connections, so it talks about bearing type bolts. I would describe bearing type bolts as bolts in clearance holes. So we expect some deformation to take place. We expect the bolt to go into bearing. Then there are two classes here, slip-resistant connections. You might describe those as preloaded assemblies, perhaps. But slip-resistant connections are working because of the friction between the two surfaces. And we will look at those a little bit later on. But for example, for the bearing type connection, we are told that we must satisfy both shear and bearing. And you can see in the other types of connections, we'll look at those a little bit later on, the things that you must satisfy. There are plenty of grades of bolts in the Eurocode. The grade of bolts that we would find most often in the United Kingdom would certainly be 8.8 and occasionally 10.9. Traditionally we would have used 4.6, but really not now. Almost always the bolt in the UK is class 8.8. So if you look on table 73, that's the table on page 73, I should have said, then you will see the formula to determine the resistance of a bolt in shear. And that's at the top of the table. So we need an alpha V factor, and alpha V is given us, it depends on the grade of the bolt. We need the ultimate strength of the bolt, and the ultimate strength of the bolt is always the first number multiplied by 100. So for grade 8.8, the ultimate strength of the bolt is 800 newtons per square millimetre. Then we need an area, and we need gamma M2. We have two choices for the area. We could either consider the area to be in the part of the bolt where there is no thread, or we consider the area to be in the part of the bolt where there is thread. So here is a part threaded bolt, and we would need to decide where the shear plane is. Is the shear plane through there, or is the shear plane through there? Because the area here is obviously smaller than in this zone. In the UK, we never have that problem because we always use fully threaded bolts. So for us, the shear plane is always through the threaded portion. And we use a fully threaded bolt because we can buy them in bulk and we can use them for all the connections that we ever find. So about 95% of the connections you can make with a fully threaded M20 by 60. So an M20 by 60 8.8 bolt is our standard bolt in the United Kingdom. And therefore, when we're working out the shear resistance or the tension resistance, we are always using the area in the threaded portion of the bolt. If you decide to do that, which I would recommend, you will always be conservative. So if you use bolts which have a length which is not threaded, if the shear plane is in that zone, then you will have a slightly increased resistance. So we are told what the value of alpha V is. We know what the ultimate strength of the bolt is. We would need to look in some table to know that the cross-sectional area of an M20 bolt through the threaded area is 245 square millimeters. We divide by gamma M2 and the resistance is 94 kilonewtons. So for us, in the UK, that value would be a value that most engineers know. They know that an M20 8.8 is worth 94 kilonewtons in shear because it's our most standard bolt. There are rules that say if you pass bolts through packing, then there is a reduction factor to be applied. So the thicker the packing, the more the bolt tries to bend, and that will reduce the resistance in shear. So the reduction factor then depends on the diameter of the bolt, D, and the thickness of the pack. So for an M20 bolt, here is the relationship between the packing thickness on the bottom axis and the reduction factor on the left-hand axis. This is a splice connection, where I'm changing from a larger section to a smaller section. This is a bearing type splice, because I have simply sized the division plate, assuming that the force is transferred at 45 degrees. So in compression, there is really no design required. But from yesterday, you'll remember that we probably have to check this splice for a tension force, a tying force. And therefore, the plates and the bolts must carry this tying force. And there may well be a problem in this area because the bolts in shear will be reduced because of the pack. So if you detail this sort of connection, you need to be aware of the reduction due to the presence of packs. That would be one of the common places where the reduction due to the packing is important. Now this is a nominally pinned connection. It has only a partial depth flexible end plate. And until the Eurocodes arrived, in the UK we would have just said there is a shear force divided amongst these bolts. And we would have simply checked the bolts for shear and the bolts for bearing. But other Europeans say when this connection rotates, some of these bolts will experience some tension. We used to ignore this in the United Kingdom. But the advice from other colleagues in Europe is that we should reduce the shear resistance of these bolts a little bit to allow for the tension. We do not have to calculate the tension, we just reduce the shear resistance. This is some advice which is not found in the Eurocode. This is only found in European design guides, but it feels like good advice, and therefore in the UK we accept this advice. And if we are designing a nominal connection, a nominally pinned connection, here is another flexible end plate, we say, okay, we take the vertical shear force, we divide it amongst the bolts, but we reduce the resistance of the bolts by 20% to allow for the tension. We do not attempt to calculate the tension. So this is just a nominal reduction. I personally do not care that we have reduced the resistance of the bolts by 20%, because in my experience, the bolts are not the weak link. Other components within the connection will be the weak link, and even if I have reduced the resistance of the bolts by 20%, that never becomes critical. So we have dealt with bolts in shear. We're going to go on to consider bolts in bearing. And if you're in the table on page 73, then we've moved down a little bit into the next part of that table. So you'll see the expression on page 73. There is the resistance of the bolt in bearing, and there are a number of factors now. So we have a K1 factor and an alpha B factor. And the K1 factor deals with the edge distance. Here it's described as the dimension E2. So is the bolt close to the edge, or is it far enough away from the edge so that the effect of the edge can be ignored? And then alpha B concerns itself with the end distance. So are we close to the end, or are we far away from the end? Are we close to another bolt, or are they sufficiently far away that they do not affect each other? So within the table on page 73, you'll see there are a number of things that we should check. When we look at the formula for alpha D, you will see that there are inner bolts and end bolts. So if this were an end plate, only one set of these bolts are affected by the end distance. So in this end plate, there would be two lots of inner bolts and one pair of end bolts. K1 is concerned with direction perpendicular to the load, and if you look on page 73, you will find bolts described as edge bolts and inner bolts. In this particular plate, all of the bolts could be affected by the edge, so they are all described as edge bolts. In this plate, which in my experience is very, very unusual, I have never seen an end plate connection that looks like this. These would be edge bolts, these would be edge bolts, and the ones in the central zone, they will be inner bolts. So that might be when you come across inner bolts. Perhaps if you can imagine this as a plan view now, and this might be the cover plate for a splice. Perhaps you put a splice in a beam, perhaps you join two sections of beam together using a splice plate that looks something like that. So we've thought about K1, we've thought about alpha B. The ultimate strength is the ultimate strength of the plate. D is the diameter of the bolt. In some of the formula you will find D0, and D0 is the diameter of the hole. So in my experience, for ordinary bolts, the hole diameter would be 2 millimeters larger than the bolt diameter. So for an M20 bolt, I would use a 22 millimeter diameter hole. And then finally there, the thickness is the thickness of the plate. So ladies and gentlemen, I know you've just enjoyed a lunch. There are not many more worked examples for you to try. But at the end of that presentation, you should find a worked example that looks rather like this. It's an end plate. It's quite a deep end plate. It's got plenty of bolt rows in it. I would like to know the resistance of the bolts in bearing in this end plate. So I believe it gives you all the data. It tells you about the dimensions. The dimensions are described as P1 and P2 and E1 and E2, so that should make it easy to use the formula. And you will find the formula on page 73 of this guide. Now, compared to the example that you did this morning of a member subject to compression and bending, this is really easy. So I do not think it would take you very long. So ladies and gentlemen, here is my view of the answer. And remember once more that you will get a complete copy of this answer later today. So we calculate alpha D first of all for the end bolts, and the end bolts are affected by the end distance, 40 millimeters. D0 is the diameter of the hole, so for an M20 bolt, the hole is 22 millimeters diameter. We calculate alpha D for the inner bolts. We calculate the ratio between the ultimate strength of the bolt and the ultimate strength of the material. And then for the end bolts, we select the minimum value, which in this case is 0.61. For the end bolts, it's slightly different. The minimum value is 0.81. And then we need to check K1, which is in the direction perpendicular to the line of action. So E2 was given as 30 millimeters. We calculate K1. Is it greater than 2.5, in which case we would take 2.5, but in our case the value is 2.12. So then we can calculate for the end bolts a resistance of 74 kilonewtons, and for the inner bolts a resistance of 98 kilonewtons. The shear of an M20 8.8 bolt we saw earlier was 94 kilonewtons. So if we apply the 20% reduction that I spoke about earlier, then we find that the design shear resistance is 75 kilonewtons. Now, ladies and gentlemen, the final worked example of the day is now ready for you. And it would be good, I think, if we could complete this one before we break for tea. So the next worked example, we've looked at the bolts in shear and bearing. I just need to tell you about welds before we can complete this example. So maybe we will do this example just after tea. I'll go back to the PowerPoint for a moment or two, and then perhaps we'll have a look at the example. So we are on page 166 of your workbook. You will have gathered that in the United Kingdom we like to do things as simply as possible. So for bolts in bearing in the United Kingdom, again we have lookup tables. We have lookup tables for S275 steel and S355 steel. And because you will have seen during that exercise that the resistance of the bolt in bearing depends on the geometry of the bolt group. It depends on the edge distance and the end distance and the spacing. So we provide two tables in the United Kingdom. One has bolts fairly closely spaced together, and the other table has bolts spread further apart. By doing that, you can increase these resistances in bearing. When you are calculating the resistance of a connection, then one of the clauses in the Eurocode is very important. The clause says that if the shear resistance is greater than any of the bearing resistances, then the resistance of the connection is the sum of all the bearing resistances. If that's not the case, you identify the minimum resistance, which might be the shear resistance or perhaps one of the bearing resistances, and then you take the total number of bolts multiplied by that minimum resistance. So let's move on then and consider bolts in tension now. Again, perhaps you would like to look at page 73 of your guide. So there are two things to check in tension connections. We must check the tension resistance of the bolt itself, that's the top line. And the second one is that we must check that the bolt does not punch directly through the material. And I will talk about that with you in a moment. Notice the highlighted comment at the bottom of this slide. The design force must include the prying action, and I will describe prying action in a moment. If you look on page 73 of your guide, you will see the formula that you now see on the screen. We need a value of K2, but the Eurocode tells us precisely what K2 is. For an ordinary bolt, K2 is 0.9. Then we need the ultimate strength of a bolt, so that depends on the class. And then we need the area, and of course the area now in tension will be the area through the threaded part of the shank. Divided by gamma M2, and the resistance of an M20 8.8 in tension is 141 kilonewtons. But what about that note that said the design force must include the prying action? We need to consider the prying action. This is the prying action, so this might be the end plate, and this might be a web, or this might be the flange, and this might be a web. But you can see there is an externally applied tension force. So the bolts feel the tension, of course, but there is also a prying force, here described with the letter Q. So let's imagine then the situation where we have perhaps a column flange and a column web, a beam end plate and a beam flange, and we are subjecting that connection to a tension. Well, the bolts carry the tension, but we also know that the flange and the end plate are going to start to yield. There's going to be a yield line running in and out of the screen along that line. So we have some moment here. And if we have a moment here, we must have a force, because the force multiplied by the lever arm gives us the moment. So that force is known as the prying force. It's normally indicated with the letter Q, and it's a geometric issue. The size of the prying force depends on geometry. So the Eurocode says you have to go through and allow for that prying force. We try and avoid that again in the UK, and we have a very simple rule, and we say as long as we observe some very simple geometric rules, then we ignore the prying force, but we downrate the resistance of the bolt in tension by 20%. So we occasionally write some technical articles where we give designers in the UK some advice. Here is one of them. This would have quite an important status in the UK. These are considered to be reliable pieces of advice. So you have some idea of the geometric limits that we're applying. There is a reference here to the prying force, and it says within these geometric limits we can ignore the prying force, but we limit the resistance of the bolt, or we reduce the resistance of the bolt by 20%. So if we do that, although we have calculated 141 kilonewtons, we take a design value of 80% of that calculated value, and we would suggest that it's easy to design an M20 bolt for 113 kilonewtons that just completely ignore the prying action. It's a simple approach, but it makes life easy for us. So again, for bolts in tension, we have lookup tables. So for an M20 bolt, there's the figure of 141 kilonewtons that we calculated earlier. So that's the tension resistance of the bolt itself. Remember, there was also the second question about will the bolt punch through the material? So could you imagine a bolt in tension pulling completely through the material with a circular failure surface? In the United Kingdom, we had never heard of this phenomena. We had never checked this phenomena, so we don't believe it would ever happen. But there is a formula. It's given you on page 73 of your guide. You can see it's something to do with a circular pattern, because there is pi, something to do with the diameter, so you calculate that distance. There is the thickness of the plates, the ultimate strength of the plates. You could use the diameter of the washer, or you could use the dimension across the nut or the bolt. And we calculate some thicknesses. This, I think, is in S275 material. So here is an M20 bolt, tension resistance of 141 kilonewtons, and to avoid the bolt punching completely through the material, we only need 7.8 millimeters of steel. So I think in the UK we would say we're just going to ignore this. This is never going to be an issue. Because if we were working a bolt so hard that we are applying 141 kilonewtons, then maybe the thickness of the material would be 20 millimeters, or maybe 25 millimeters. It certainly wouldn't be 7.8 millimeters. So now is 3 o'clock, ladies and gentlemen. I suggest now we break, and you can look forward to the worked example when we return. I am on page 172 of the workbook. 172. So there is a relationship if bolts are in combined shear and tension. It's a very simple interaction. and that's the only check that we need to perform. So we will leave ordinary bolts and we'll move on to preloaded bolts. And in the UK, these are like death warmed up. So we would not like to use preloaded bolts because we think it makes the connections very, very expensive. So preloaded bolts work by clamping surfaces together, and they work on the principle of friction between those two surfaces. So the two surfaces will be shot blast, they will not be painted, they will be protected. The protection will only be removed as the steel is erected, and then the bolts have to be tensioned in a very careful way. The only times that we would use friction grip connections are when slip must be avoided. So for us, 95% of connections are ordinary bolts in clearance holes. Friction grip connections are relatively uncommon. How do we know that we've got the right tension in a bolt? Well, maybe we use one of these special washers, so as you tighten up the nut, the dimples in that washer begin to crush, and you measure the gap with a feeler gauge. I have never seen these used in the UK, but when you tighten the bolt, these resin reservoirs, they burst, and you get this red content appearing down these little channels. This sort of bolt is becoming increasingly used in the UK. So here is a real-life example of a tension control bolt. And there is a special piece of equipment which holds onto this end of the bolt and turns the nut. So you don't need to have any equipment on the other side of the bolt. Yeah. And at the appropriate tension, this part of the bolt shears off. So they're very easy to use. You don't have to measure anything, and they are used very commonly in the UK. So back on page 73 of your guide, back on page 70 of your guide, 70, then down at the bottom of the table it tells us the rules about slip-resistant connections. So there are two categories. Category B, non-slip under serviceability loads. We need to check the shear. We need to check bearing. We just follow the rules in the code. Category C, non-slip at ultimate limit state. So again, we need to check the slip resistance. We need to check the bearing resistance, and we need to check the net area of the connected part. And we are surprised about this one, because this assembly is non-slip at ultimate. It should never go into bearing, because non-slip at ultimate means you never reach bearing. But nevertheless, the Eurocode says we must still check the bearing resistance. So for all non-slip connections, you will see the formula. You will have that in your guide. There is a factor, first of all, which is to do with the slip coefficient. There is a factor which concerns the number of surfaces which are being joined together. And the final term here is the preload in the bolt. And all these things are given us in the Eurocode. So the KS factor depends on the type of hole. So is it an ordinary hole or is it a slotted hole? And we immediately read the KS factor. Then we need the factor which governs slip resistance, the slip factor. So there are a number of slip factors for surfaces A, B, C or D, but we need to look somewhere else to decide what A, B, C and D represent. So we would look in EN 1090 part 2, and that tells us, for example, that surface type A the surface has been shot glass. That will define for us the slip factor that we use then in the calculation. Then all we need is the preloading force. So again, we could look in 1090 part 2, and for different bolt diameters, we can immediately read off the preloading force. We can calculate the preloading force if we wish, and the Eurocode tells us how to do it, but this table within the Eurocode gives us precisely the same answer, whether you calculate or whether you just read from the table, the same answer. When we're calculating the slip resistance, notice slip resistance for category C or category B, a different value now. Instead of gamma M2 that we were interested in earlier on, we've now got gamma M3. And we have two values of gamma M3. Gamma M3 or gamma M3 SER, and the SER stands for serviceability. The values are recommended as 1.25 and 1.1, and the Ukraine National Annex accepts those values. So category C then, let's imagine we have bolts in ordinary holes, so the KS factor is 1. Let's imagine we have a surface A, so the slip factor is 0.5, gamma M3 is 1.25, and therefore we calculate the slip resistance of an M20 bolt to be 54 kilonewtons. Category B, same expression, so same preloading force that we've just seen, but now we're using gamma M3 SER. And I apologise, ladies and gentlemen, about this slide, because that should be gamma M3 SER. So if you're keeping pace with me in the notes, maybe you ought to add comma SER. I hope that's clear. So here's an example then, a numerical example. Let's imagine that we have a shear force on a connection. We know that we have some load due to the permanent actions, some load due to the variable actions. I need to know those proportions because I need to work out an ultimate shear reaction and also a serviceability shear reaction. Serviceability, there are no gamma factors, so I can simply add the forces together, and therefore at the serviceability limit state, my shear force is 382 kilonewtons. Divide by the slip per bolt, 62, and the calculation tells me that I would need 8 M20 bolts. If I calculated non-slip at ultimate limit state, then I need to factor these shear forces. So my ultimate shear is now significantly more, 550 kilonewtons. I have a different value per bolt, because remember this depends, is it gamma M3 or is it gamma M3 SER? So a different value here, and for this different category of connection, apparently I would need 10 bolts. So easy way, but remember in the UK, we would like to avoid preloaded assemblies because we think they are expensive and we think they are inconvenient. So let's move on to welding then. Welding is one of the most expensive operations for a steelwork fabricator. So there would be a big drive in the UK to minimise the amount of welding. It's time consuming and it's expensive. In the UK, we always specify a weld by the leg length. I believe that's the same in Ukraine. Some countries specify a weld by the throat. So if you are working in different countries, you should be careful. My view is that 6 or 8 millimeter legs are very standard fillet welds. You can create a 6 mil or an 8 mil fillet weld in one pass. If you decide that you need a 10 mil fillet weld, for example, that will be 3 times as much effort. If you decide that you want a butt weld, you are making your steelwork very expensive, because the plates will have to be prepared. It will be a very expensive operation to weld a butt weld, and then there will be expensive testing. Perhaps the testing will not be carried out until 48 hours later, because you are concerned about cracking of the weld. So as soon as you start to specify butt welds, fabrication starts to become expensive. A steelwork fabricator should have a weld procedure for all the welds that they're going to create, because brittle fracture, you have specified the material yesterday, you wish to ensure that the welds do not behave in a brittle manner. The risk of brittle fracture in a weld depends on the carbon equivalent value of the steel, it depends on the heat input into the weld, it depends on the combined thickness of all the materials meeting at a particular connection. Because if you have lots of material, then the heat will escape very fast. So all these bits of information go towards creating a weld procedure for the steelwork fabricator to say, that's how I'm going to create the weld so that I minimise the risk of brittle fracture. As well as the weld procedure, you would need a welder who is qualified to weld in the appropriate position. So welding vertically down is straightforward. Welding overhead is much more difficult. So you need a welder who is able to weld in those positions. Not any old welder, but a welder who is qualified working to a weld procedure. So 2 days ago I was discussing with colleagues in Ukraine about whether connections should be welded or whether they should be bolted. I believe site connections should be bolted. Very expensive to weld site connections. Access, safety, weld procedures, protection to avoid from the weather, subsequent inspection are all very expensive. So the resistance then of a weld is to do with the length of a weld and to do with the throat thickness. And the length of the weld, the Eurocode says, we take the actual length of a weld and we reduce it by a little amount at each end. The Eurocode says we reduce it by a throat thickness from each end. The UK practice, we reduce it by a leg length each end. And why? Because when you strike the arc and when you stop the arc, that's where you're likely to get imperfections. So in design terms, start and stop are avoided. They're neglected in calculation. So some people say, well, I'd like to do an intermittent fillet weld. So perhaps 200 millimeters of weld, no weld. 200 millimeters of weld, no weld. Maybe it's a good idea, but remember there are many starts and stops if you choose an intermittent weld. So the steelwork fabricator I work for, we would much rather lay a continuous weld to avoid the starts and the stops, because there faults can appear. The Eurocode then has a directional method to calculate the strength of a weld, and it also has a simplified method, and I would recommend the simplified method. The strength of a weld depends on the weld strength and the throat dimension. And the Eurocode tells us precisely how to calculate the weld strength. So Fu is the ultimate strength of the material. We have a factor beta W, which depends again on the grade of the steel, and we have gamma M2, and from earlier this afternoon I hope you will remember that gamma M2 is 1.25. So for different material strengths we have different values of beta, and therefore we have different weld strengths. And we would simply take that weld strength, multiply it by the throat thickness, and that would tell us the resistance of the weld. The resistance that we've just calculated is the longitudinal resistance, and transverse welds are a little bit stronger. So if you'd like to have a look at page 79 of this guide, you will see a formula on page 79 which is exactly the same as this. It depends on the angle theta compared to the direction of the load and the throat of the weld. So for a standard fillet weld, theta is 45 degrees, and you find that a transverse weld is 22.5% stronger than a longitudinal weld. So this is a UK example for which I apologise. Oh no, it's a Ukraine example. S235 steel. We work out the weld strength, which you saw on one of the previous slides. We know that for a 6mm fillet weld, the throat is 4.24 millimetres. So longitudinally, a 6mm fillet weld, 0.88 kilonewtons per millimetre. Transverse weld, a little bit stronger, 1.225 gives us 1.08. And I would suggest that for the standard welds, you create a resistance table. So for 6mm fillet welds, this is in the UK, this is in S275 material, we know the strength of a longitudinal weld and a transverse weld. So, I'm not going to ask you to do the worked example now because I want to talk about portal frames and light gauge steel. But there is our connection. We've been thinking about the bolts in shear, we've been thinking about the bolts in bearing, we've been thinking about the weld, all straightforward, all very easy. The final thing that we need to check is the local shear over that zone. Because, okay, we can get the load into the weld, but then from the weld into the web of this beam, we need to check the local shear. And we would check the local shear by using the formula on page 44 of this publication. So maybe you will have a look at page 44. So at the bottom of page 44, you will see this formula. Shear resistance is the shear area, yield, divided by gamma m naught. The question is for a rectangular area. So there is a rectangular area which has the height shown, but the thickness of the web, what is the shear area? And our recommendation is you take the web thickness multiplied by the height shown, but then use a factor of 0.9. That would be the factor that we would have used in previous standards. Now, in my experience, the resistance of a simple connection, I'm not going to ask you to do this works example, the resistance of a simple connection is almost always dominated by the resistance of the web in shear. Not the bolts, not the plate, not the welds, but the local resistance. So in the works example that you will get at the end of today, you will see the calculation and you will see that the local shear resistance is much lower than the bolt resistance, much lower than the bearing resistance, much lower than the weld resistance. Plates in tension I'm going to go through fast because I spoke about it yesterday. So here is the situation that I attempted to draw yesterday on the flip chart. And just a little reminder, there are two checks. There is one check which is of the gross area, and that uses the yield strength. And there is a second check of the net area, that uses the ultimate strength of the material, but remember, there we use the value gamma M2. And again, you will find that in your guide. So nominally pin connections then, and I will talk about the UK practice. Those are the two almost universal connections, an end plate detail or a fin plate detail, and they would be at least 60% the depth of the beam. Even if that meant that I was providing more bolts and more plate and more weld than I needed to carry the force, they would always be at least 60% the depth of the beam. So there are some partial depth flexible end plates, not welded to the flanges. There is a flexible end plate, but that has been welded to the flanges. There is another flexible end plate, again has been welded to the flanges. Here are fin plates, so a very, very common connection used with enthusiasm because the secondary beams have simply been cut and drilled. There is no fabrication of these secondary beams. There is no welding. So this is a very efficient way to arrange beams. So there is a fin plate. The fin plate has been welded to the grey beam. The yellow beam is the supported beam. There again is a fin plate, although the fin plate is on the other side of the web. And there again is a fin plate. So really simple, cheap, but effective connection details. So that's simple connections. I'm going to move on now to moment-resisting connections. And the Eurocode says that we have two options when we consider moment-resisting connections. We can assume that the distribution of force is linear, which would be a very traditional way of arranging a moment connection, or we can assume that the distribution of bolt force is plastic. The distribution of force that the Eurocode promotes is really a plastic distribution of force. So this is a linear approach. This would be a very traditional approach. It's assumed that the compression is applied at the bottom flange. So if you imagine on the right-hand side of this screen there is a beam, the bottom flange is at this level, the assumption is that it rotates about the bottom flange. These horizontal lines are lines of bolts, so in this connection there are 3 rows of bolts. Each row perhaps has 2 bolts. So you simply allocate a tension to the top row of bolts. We don't know what the tension is, it's unknown, so here it's described as T for tension. Then we say, okay, the force in this row of bolts is just determined on the basis of the proportion from the centre of rotation. And then we say the force in the bolt multiplied by a lever arm gives us the resistance. We add the resistance for each row of bolts. The only thing that we don't know is the tension T, and so we say the resistance is equal to the applied moment. We solve that expression and that will give us the force in the tension bolt. And we simply then choose a bolt which can carry that tension force. Very simple, very traditional, absolutely unreal. Connections do not behave in this way because this presumes that all the bolts are perfect springs and presumes that the rest of the connection is entirely rigid. And that's completely wrong. The Eurocode says we can do it if we wish. The Eurocode approach is to say we will allow the bolt force to reach the resistance of the row. So in this particular example, you'll see there is an extended end plate. The extended end plate is relatively thin, relatively weak. So once the bolt has reached that sort of resistance, indicated by the top arrow there, it then starts to yield, and it doesn't accept any more force. The next row of bolts is in a fairly stiff area. It's got the web, it's got the top flange, so it attracts a lot of force. And the force in that row of bolts increases until something starts to yield, and then force is distributed to the next row. So that will be a plastic distribution, and this, if you test the connection, is typical of the distribution of force. So this is a realistic distribution of force. The plastic distribution demands that something yields to allow that plastic distribution to take place. What's assumed that yields is either the end plate or the column flange, so something flexible. You must protect the welds, because the welds do not behave in a plastic way. They are relatively brittle. So within certain limits, the Eurocode then allows this plastic distribution. One of the key benefits of the Eurocode is it takes the complex arrangement of yield lines, which is a three-dimensional arrangement of yield lines, and converts it to what the Eurocode calls an equivalent T-stub. So this is a rather two-dimensional arrangement. You imagine this T-stub being subject to a tension, and you imagine that it's going to yield, maybe at the root radius and maybe on the bolt lines. So as we look at this particular diagram, there are 4 yield lines, one on each of the bolt lines and one adjacent to the root radius. This T-stub has a length, so we can calculate the resistance of the yield line because we know the thickness of the flange and we know the length of the yield line. So a three-dimensional difficult problem has been converted to a two-dimensional problem, which is easy for us to calculate. So the Eurocode, first of all, looks at this arrangement of bolts, and we calculate the length of an additional T-stub. I would like to say that last sentence again. We don't calculate the length of an additional T-stub, we calculate the length of an equivalent T-stub. And then for each one of those T-stubs, we must check which mode of behaviour. Is it a thick flange and rather weak bolts? Is it a thin flange and rather strong bolts? Or is it somewhere in between? So the Eurocode then gives us many formulae to calculate the length of equivalent T-stub. So here is a selection of formulae. They are generally geometric, so they concern themselves with the geometry of the connection. Within the process, you are allowing for this prying force Q. And the Eurocode says, for moment connections, the process allows for the prying force. Within the formula, there are many references to a value of alpha. And alpha is used if the bolt, in this particular diagram, is next to a web, but also next to a stiffener. So you would get a very complex three-dimensional yield line pattern, and the Eurocode uses this alpha chart to determine the resistance of a bolt in those locations. Unfortunately, in my view, the Eurocode does not give you the formula or the expressions to calculate these curves. You can develop your own expressions, and that's exactly what we have done in one of our guides, so that we can program it into software. The checks in the Eurocode are very comprehensive. Here you have an indicator of the sorts of checks that you will carry out. So my recommendation is give it to the youngest person in the office or use software. First of all, we calculate the resistance in the tension zone. So are we limited by the resistance of the bolt, or the beam web, or the end plate, or the column flange, or the column web? One of those will limit. And that will establish the resistance of the tension zone. But you know that as you pull in tension, there must be an equal and opposite compression. And therefore we need to consider things in the compression zone. Will the web of the column fail in bearing or buckling? Will the shear in the column web panel, because you have a tension at the top and a compression at the bottom, that's applying shear in the column web panel, will that fail? And will that limit the resistance of the connection? So really, I'm trying to encourage you to observe that if you are going to do many connections that resist moment, I believe that software really is the only realistic way forward. Bases in the Eurocode are very easy. They assume an effective area which will have the same profile as the piece of steel. And you calculate a cantilever, and the cantilever is the same dimension all the way round the profile. And then you imagine that this cantilever has got a uniform load, that will be the base pressure, and you simply then determine the thickness of the base. A very straightforward approach. So here are some base details. This, I think I showed you yesterday, would be very typical in the UK. The base practically is going to be set on some steel packs here before later this grout is introduced into the connection. Sometimes I worry about the quality of our base details. I am not sure that they are high quality always. Sometimes I worry a lot about the quality of our base details. Sometimes I am not convinced that we would be able to do a high quality job of grouting the base plate. Sometimes I look at details and I see on the left hand side a huge bracing with 6 bolts, and therefore there must be a large force in that bracing. And then I look at the detail and I see 4 holding down bolts. How can that possibly be correct? And then I see a large base with a huge bracing, and I see a very large gap, and I see a man poking cement under here with a piece of stick. And I worry about the details of our bases. So maybe if we have a serious base shear, a horizontal force, maybe we would weld something to the underside. The people who cast the concrete, if you ask them to cast a recess in the concrete, they will be very angry and they will want to know where you live. So I would think carefully before you do that detail. This is a bearing type splice, so a very ordinary detail, cover plates, a division plate, and beware, because there are packs. Packs reduce the shear resistance of the bolts. This sort of detail is becoming more common in the UK. So an end plate and a base plate and just 4 bolts. For a more traditional version, you can see I am concerned about the reduction in shear. Take care if you are introducing packs into the detail. Now this is a bearing type splice, and I've said before, we believe that the force is transferred directly between the flanges. That does not mean that you need a perfect fit. So here is an extract from a specification in the United Kingdom. This is for, the English words here are ends prepared for bearing. So we imagine this is going to be used in a bearing splice, and it allows a gap. So we don't need perfection even in a bearing detail. Here is the tolerance during erection. So again, the English words are the gap between bearing surfaces. So we've designed it as a bearing connection, and yet we are allowed a gap. So the rule in the UK is if you have cut this with a saw, then it's good enough. If you have burnt this, I'm not sure how we're going to translate this, ladies, but with an oxyacetylene torch. Did that make sense? A burning torch. Then the edge is very uneven and would be unacceptable. But cut with a saw and it will be okay. The Eurocode has some very important rules for splicers. For a bearing type splice, the rules are not very onerous. We would need to check the splice in tension if we have some tying forces applied. For non-bearing type splicers, so they would be splicers where there is a physical air gap between the two sections, then I would warn you that the rules in the Eurocode are very, very onerous. Because the rules say that we must provide enough material, that the material must be based on the section capacity. So if you had a splice where the applied force was only 10 kilonewtons, so something very small, the rules in the Eurocode say, well, the minimum resistance is not based on 10 kilonewtons, but is based on the capacity of the member. So for non-bearing type splicers, the ones with an air gap, you do need to worry about these rules. I think they are unreasonable. So in the Eurocode you will find the clauses. You underlined in this top part of the clause, this is English I know, it's referring to 25% of the moment capacity, not the applied moment, but the moment capacity of the member. And you would have to make sure that your splice has resistance in both axes. So for a non-bearing type splice, that would be very difficult, I think. For bearing type splicers, we have some standard details, and they would be used in the UK. So, moment resisting splicers. So here my arms are representing a beam, and I am imagining that we want to join two beams together and we want to provide a splice. And the common way to do that is to assume that the moment is carried by the flanges. So we take the applied moment, we divide by the lever arm between the flanges. That will give us the force in the flange. We can then design the bolts, we can design the cover plates. And then commonly we would say that the web plate just carries any shear. I think that would be common for most designers. The Eurocode, however, says, and I will read this in English, that the parts subject to shear, so that would be the web cover plates, they must carry the proportion of moment carried by the web, irrespective of any shedding of stress into adjoining parts. So even if you have designed the splice to carry all the moment on the flanges, it says that you must design the web plate not only to carry the shear, but also to carry the moment associated with the web. For me, that would be an important change in practice. This is a detail where we have a beam welded to a column. So we would imagine that in this diagram, the top flange is carrying the tension, the bottom flange is carrying the compression. We would need to check the web of the column to see whether we are going to fail in crushing or buckling. We would need to check the web of the column because we are applying a shear to this web panel. We also would need to check the web of the column in the tension zone. The Eurocode also has some very clear rules when we weld a member to an unstiffened flange. So this is a plan view of the previous diagram. This is the top flange of a welded member. This is a cross-section of the column, and there are no stiffeners in here. This is an unstiffened connection. And the Eurocode says we must calculate an effective breadth because this area is stiff, being adjacent to the web, and this area is relatively flexible. And so the stress distribution is very irregular. The Eurocode says we do not want to deal with an irregular stress distribution. We want to deal with a regular stress distribution, and that leads us to this concept of an effective breadth. And the effective breadth is something to do with the thickness of the web, something to do with dispersion through the thickness of the flange. And that's an important concept, and you will find that in very many connections, that the only effective part is the part of the connection adjacent to the stiff area. Sometimes designers call these stiffeners. I would describe these as strengtheners, because somebody has given me some beams and columns which are inadequate. They are not adequate to carry the forces. And as a steelwork fabricator, I have to strengthen them. And I would like to avoid that costly exercise. If I were the designer of these connections, perhaps I would select a slightly heavier column to avoid the expense of this strengthening. So in the UK, it is always considered that minimum weight is not minimum cost, because minimum weight means that you end up strengthening the detail. If we need to check the column web in compression, then we need to check for local crushing, and we also need to check for buckling. And there are rules then in the Eurocode that tell you how to design a stiffener. We're just going to work out the properties of this cruciform section. We're going to design it like a strut, like we did yesterday. So you can see, ladies and gentlemen, that I get rather excited about stiffeners. My view is that they should be avoided because they are expensive, they are disruptive, they clash with beams coming in the other direction, and I would try very hard to avoid them if I could. So moving on, the Eurocode also tells us about when we connect hollow sections to hollow sections. So for example, if we were designing a truss, we might choose a hollow section because hollow sections look beautiful. There are lots of design guides published by an organisation called SIDECT. The guidance in that range of publications has been brought into the Eurocode, and you will now find it in 1993-18. And the rules that you find were on the basis of tests. So the scope of the rules is limited to the test programme. So there are lots and lots of different failure mechanisms which were tested and rules were developed for them. So many, many different formula which look rather like this. They are generally empirical formula. In the UK, if we had to design a joint like this, we would give it to the youngest member of the office, or we would use software. So I would recommend that you use software. I think the serious point to make is that nearly always the resistance of the joint will be less than the resistance of the member. So if you are not careful, you will be providing a design which demands strengthening, and that will be expensive. When I practiced as a steelwork designer, if I was designing a truss in hollow sections, I would complete an initial design, and then I would check the joint resistances and make sure that they were adequate. And perhaps I would have to change my choice of members to make sure that the joints could be fabricated without strengthening. Because to strengthen a hollow section joint is very expensive, particularly if you have chosen circular hollow sections. How do you connect to hollow sections? Well, a fin plate would be a good idea. Very easy to use a fin plate to connect to square hollow sections or rectangular hollow sections. Sometimes people use these expanding anchors. A number of years ago, there was an idea that you could use flow drill. So a mandrel is forced through the wall of the section. It produces this material on the inside of the section, and then you cut a thread into that material, and then you can place an ordinary bolt in that hole. Not used in the UK because the equipment to drive this mandrel through the material is very expensive. Many people use these bolts in the UK for hollow sections. These are called blind bolts. So you can see that they have a piece of metal on a pivot, and you put the bolt in, turn the bolt, the piece of metal rotates, and then you can pull back against the inside of the hollow section. So these are in quite common use now. Remember, if you're putting tension into a hollow sections almost always have very thin walls. It's likely that deformation of the hollow section will be the key design check. It's not likely that the bolts will be the weak link, or the end plate, or the weld, or this web. It's almost always going to be the deformation of the hollow section. So bracing connections, two sorts of bracing connections. This would be very common. An end plate on a, in this case, circular hollow section, a stem, and bolted to a gusset plate. For heavier loads, perhaps the plate is going to be cut into the hollow section. So there would be an example of the second type of detail. Here is a circular hollow section. The plate, you can see, has been cut into the hollow section and then re-welded. Useful, I think, for higher loads. Here again, same detail. Plate has been cut into the hollow section. Lots of bolts, so presumably quite a heavily loaded connection in that case. Again, the same detail. Now, we've seen this slide before, and sometimes when you look at details, you just know things are wrong. The base plate looks wrong to me. If we need 6 bolts to carry this force, then I think this is an unusual detail for such a high force. I would have expected this detail perhaps to be a plate cut into the hollow section, like we have seen before. So this to me is a little bit unusual. If we have a more modest sized bracing member and perhaps less bolts, then the detail with an end plate and a T perhaps connected to another plate, that would be more common. So this concept then of effective breadth that we saw earlier on applies to these sorts of details. We know that the force is in this plate, it's been transferred to this plate via the bolts. How does it get from this plate into the bracing member? Well, it goes through the welds, of course, and those would be transverse welds, not longitudinal welds. But then the force is going to spread, and it's going to spread depending on the thickness of the end plate. So there are rules that say this spread is considered to be at 1 in 2.5, and that will establish the dimension of that effective width. So now I'm looking down my hollow section here, and the parts in green are the elements that fall within the effective breadth. And I ignore everything outside. So I neglect anything outside the effective breadth. So personally, I would design the weld just on the length of weld that falls within that effective breadth. And I would check the wall of the hollow section locally just over the width that falls within the effective breadth. That's my advice on how you should design those connections. And then for the stem itself, then we will have 2 checks to carry out. We will have a check on the gross cross-section. We will have a check on the net cross-section. We will check the bolts in shear. We will check the bolts in bearing. This would be the other sort of detail. Of course, we would need to check the bolts in shear, the bolts in bearing. We would need a gross area check. We would need a net area check. And then we also need to determine the length of weld on this side of the plate and on the far side of the plate. So for large forces, I think this sort of detail is very effective. And then we have to design the gusset plate. And certainly in compression, you need to take care because the gusset plate may well buckle. So many people take the force and they determine the 2 components of force, and perhaps they would design the weld for the horizontal component and the world for the vertical component, but you still need to worry about buckling of the gusset plate. Because I am afraid to say in the UK we have had a couple of examples of the gusset plate in compression buckling. So in the UK we now have new rules for the design of the gusset plate, because probably our old rules were not adequate.